Welcome, everyone. You have joined Using Realistic 3D Simulation to Enhance Teaching Machine Control Programming with Wayne Schaefer, an electrical controls engineer with 35 years of experience in programming and troubleshooting a wide variety of PLC, CNC, and robotic systems utilized in machine casting, assembly, and testing equipment. Wayne possesses a strong aptitude in electronics, power systems, mechanical apparatus, and manufacturing processes. His career with General Motors provided exposure to industries around the world, culminating in a 4-year assignment as the lead controls engineer in Thailand, building a new diesel engine plant. Wayne is now a full-time professor of industrial automation at Niagara College, where he developed and is now teaching courses in robotics, AutoCAD, PLC systems, and project management. Please note there will be a Q&A period after the presentation. Please submit your questions at any time by typing them into the Q&A box to the right of the screen. OSPE staff will field as many questions as possible. Now, please join me in welcoming Wayne.
Hello, my name is Wayne Schaefer, and today I want to talk to you about using realistic 3D simulation to enhance teaching machine control programming. There are several items I'll be covering here, including the traditional approach to education and training, a brief discussion on simulation tools. We'll look at a detailed overview of the software used to create a simulated factory, and we'll top it all off with a demonstration of a functional simulation. If we take a look at the Universal Design for Learning concepts created by the Center for Applied Special Technology, or CAST, there are a variety of elements to consider when discussing how to best convey information in the classroom. This applies to traditional education institutions as well as industrial settings. So my focus is in that bottom middle element, which is providing options for comprehension, such as activate or supply background knowledge, highlight patterns, critical features, big ideas and relationships, guide information processing and visualization, and maximize that transfer and generalization of information. So how do we accomplish this when we're teaching PLC programming? Now, before we look at the simulation, let's take a quick look at the teaching dilemma. Everybody in industry knows the fun part is all about programming and coding. Those of us that love to program just want to get our hands on the keyboard as soon as possible. And although programmers are great at creating code, they don't always see the big picture, and project managers are not always in tune with the needs of the programmer. So this is why we get hung up on the programming portion and kind of forget to tell the students why they're doing it. So as a reality check in a typical teaching environment, we give the students programming to create, but do very little in detailing where he or she fits in the project in reality. So here's a Gantt chart, typical Gantt chart, durations, timelines, milestones, interconnections, that sort of thing, all nicely laid out. But where we teach is somewhere in the middle. And breaking that down even further into the programming lifecycle model, we tend to be right here in the middle of that model as well. So it's a very small part of the project, and this is, again, where programmers enjoy programming, and this is what we typically teach. So many of us have used the model garbage in, garbage out as a concise way of reminding students that a computer just processes what it is given. And if you're not spending a large amount of your project time in planning, designing, and flowcharting your code, you're destined to be one of those who this refers to. My point here is that, again, we tend to focus on creating the program, not an analysis of the input data or even looking at the results we are trying to achieve. So let's take a look at the traditional approach to PLC learning. Here's a common trainer I found on the internet. And don't misunderstand me, having hardware is a great place to begin, and it's an absolute necessary step in the learning process, especially for those who have not been exposed to this type of hardware. So Hardware Simulator demonstrates physical connections, interconnections between modules and components, allows them to do hardware file updates, configurations and settings within the PLC, and we still deal with real inputs and outputs. So this will always be required. But what's missing is that ability to relate to a real machine or factory, to have a goal or task-based lesson to keep the student interested beyond just, push buttons and lights. There's no good demonstration of automatic and manual functionality, and we don't have an HMI function related to actual machine controls to show the students. So what we need is an additional method to better meet the needs of these students. We want to provide that better comprehension by example and demonstration. But how do we provide that visualization, that background knowledge, discuss patterns, critical features, big ideas and relationships like in the CAST criteria? How do we maximize this transfer? And one solution I've come up with is to expose the students to real machines or automation. However, in the classroom, we can utilize a pre-built, fully configured and programmed simulated work environment. And I will discuss this further and also demonstrate what I'm talking about. Now, we all know that simulation's been around for decades. Virtual and physical simulation has been used in medical fields, mathematics, architecture, aeronautics, space, and much more. So why do we simulate? Well, we simulate because it gives us the ability to test theories, designs, and virtually because it's safe and cost effective. We do this without risking equipment damage or, more importantly, human life. With that being said, there's definitely a need for specific criteria or that simulation isn't valid. Simulation must have that ability to link actions and reactions of the model to the real world. For example, we would want a medical mannequin reacting the same way as a real person. When you're doing AR, CPR, defibrillation, or even childbirthing, it's critical, which is critical for first aid and medical training, that mannequin or device must have that ability to react the same way as a real person, or the medical technician, so the medical technician can learn exactly how to perform tasks under stress. Aircraft simulators must encompass all the complex inputs and reactions of a real airframe in flight, and we use algorithms to tweak energy usage of electric and hybrid electric vehicles. What's also a very nice critical component here of simulation is that ability to collect information. And analysis of that provided data can be utilized to not only improve the model, but also the software device or person being subjected to the test. So similarly, we want to model real-world aspects of equipment in our simulation for PLC training, including physical behavior such as acceleration and velocity of components, some type of reaction to simulated objects, that ability to relate this to real controller inputs and outputs. And the objects in the simulation itself must have the ability to be manually manipulated, picked up, thrown around, that sort of thing, exhibit some sort of randomness as real world objects, have mass and act accordingly, and observe some physical rules. So let's take a look at a machine or factory simulation. There are quite a few simulators available, but I've been focusing on a piece of software called Factory IO. Now, it's not a sales pitch. This just happens to be the software I picked while exploring better training methods while working at General Motors. When I was on assignment in Thailand, for an example, I used Lego Robotics to teach programming to my engineers, but that's a story for another time. So back to Factory IO. It does meet many of the criteria that I listed previously. It's user configurable and flexible. It has that ability to start with one level of difficulty, but can also be enhanced to be more challenging and complex by adding objects and equipment. It has that ability to create and work with assemblies as well. So there's a lot of videos on YouTube that you can watch. As you can see here, the simulation meets the requirements that the model should have real-world aspects of equipment, including physical behaviors. It has acceleration and velocity components. There's sound, a decent 3D representation of the equipment. The reactions and interactions of the simulated objects within the simulation are realistic as well. In this video, the green, blue, and raw material is converted in the CNC into what we call lids and bases that then can be fitted together as an assembly. The objects slide along the conveyor and they interact with the rollers as if they were real equipment. What you maybe missed at the beginning here is the material is actually filtered with a camera, and we'll talk about the camera later, providing that ability to control delivery of parts. So after the CNC creates the lids and bases from the raw material, they're sorted, assembled, and then dropped into a bin. Now, this particular factory removes the assembly immediately as it enters the bin, but you could also add more conveyors and move that box of assemblies into a storage facility, which you're going to see an example in the next video. The nice thing here is it's relatively simple, but also has enough complexity to look like a real factory. So as I mentioned, it meets many of the criteria that I listed previously. And we can start with one level of complexity and build up by adding more features and equipment. So here's another video showing a warehousing operation. I did speed it up a little bit to make it a little bit more interesting. All the material in this video has simulated weight. The pallets and boxes, if you put too many boxes on top of each other, the pallet can slip on the conveyor. If you pile the boxes too high, the boxes can actually jam up going into the pocket, or they could fall off as that gantry moves back and forth. So it meets that criteria that we're looking for, that objects in the simulation act like real world objects, or not just stuck in place. So briefly, Factory.io does provide a nice collection of parts. There's more than 80 parts, including some machinery, material handling, conveyors, there's manipulators, there's general build items, such as decks and walkways, that sort of thing. And there's various size boxes and pallets, as well as machinable material that you can use. And of course, there's a good selection of sensors, indicators, operators, and warning devices. I'm going to show you quickly all of these over the next few slides. So shown here are some of the transferable objects that can be put inside the simulation and move inside the simulation. But the boxes not only come in various sizes, but they have unique weights, and you can use these weights inside the simulation. And as you saw in the previous video, there's pallets and storage containers to put some of these items inside or on top of. There's 3 objects used to simulate machining. There's raw material, there's bases and lids in different colors and in different materials. They can be used in the CNC and robot simulation, and they're unique again in that they can actually be assembled together, and then once you've assembled them, they stay together as an assembly. But you can also create any of these individually using the emitter function that's in Factory.io. You don't have to go through the CNC machine to create the lid or the base. You can just create it and keep the simulation simple. There's also an assortment of standard sensors available that can be placed anywhere and in any orientation. And the detection is not limited just to those previously shown boxes, pallets, and machinable parts, but you can use it to detect any part of the apparatuses that are moving inside the simulation, such as a pusher on the elevator, a door, a diverter, or even the elevator itself. And I'll show you some of this in the demo. The demo has some of these extra sensors to enhance those built-in machine capabilities that Factory.io comes with. The capacitive inductive sensors have additional feature of being able to output a value if you want via an input word to the PLC to indicate how close an object is to that sensor. So that's kind of a nice feature. There's also a light array made up of a sender receiver pair. It has multiple outputs that can be used for object height detection, and there's a retroreflective and diffuse optical sensor available. Now, they have a recent addition of an RFID reader and a vision sensor, and I'll get more into that in the next few slides. There's a group of operators that are called emergency. There's a group of operators we have. There's an emergency maintain push button. You push it once to set, push it once again to reset. There's an assortment of blue, green, yellow, red indicator lights, green, yellow, and red backlit push buttons. And just FYI, the red push button is normally closed, so like a real stop button would be. There's also a 2-position selector switch and a potentiometer available. Of course, there's a control box that you can use to mount all these indicators on top of to make it more realistic. Under the warning device category, we also include the addition of a warning siren, a 3-stack pole light, and a rotary warning light. And that's pretty much all you need for these simulations. There's not a whole lot more that needs to be added. Now, there's a variety of non-active components such as handrails, stairs, decks, plating, and pillars in order to build platforms. There's fencing sections that can be used for enclosures, including a safety gate and a fence section the conveyor can actually pass through, adding more realism to the simulation. If we take a look at some recent additions, there's an RFID sensor in the form of a read-write head and RFID tags that are placed on the boxes, pallets, and on the container. That RFID head can be used to read or write the data to any of these RFID tags as long as they're within 0.5 meters of the head. One tag can be detected at a time, and if there's more than one tag in the field, both or one of the tags will be ignored. So very, very much like a real-world RFID would act. What is useful here is that RFID tag includes 128 double data words of free memory and a unique serial number. The unique serial number is sequential, generated when the tag is created, but that 128 words of memory, it's user writable and readable, and stays with the RFID tag throughout the simulation, no matter where that box or pallet is. So you can provide tracking inside your factory. The vision system, a little bit different. It consists of a vision camera and a barcode placed on those blue, green, and metal materials. When one of those objects is in the camera sensing area, the camera will output either digital or numeric value, whatever you select, that represents that object. And in that one simulation, there was a camera at the beginning that was used to sort the blue and green material as it came into the simulation. Another recent addition is the encoder feature. It can be turned on or off. and you can put this on any one of the motors in the simulation. The output is simply the on-off transition of each of the two traditional encoder phases, which is kind of cool. It creates that opportunity to discuss original encoder design as opposed to the current applied serial, parallel, or Ethernet high-speed communication technology that we use now. So I found that very challenging for the students. Now, if you're just starting out, you have a wide variety of scenes to choose from. You've got a pre-built model, including everything from moving a box along a conveyor to sorting materials to filling a tank with fluids. There's also an automated warehouse, as you saw, a pick and place, and a CNC production cell, including load and unload robotics. Now, some of these scenes, such as the CNC cell, have reduced complexity. You don't have to program the robot. You just give it a go signal and the robot functions. So they did try to keep it so it didn't become overly complex. Now, the basic scenes are useful for basic training, but what I did was go even further to convey that look and feel of a real automated system. Again, the goal was to develop a simulation that can demonstrate the concepts needed for industry. Now, unfortunately, a simulation with even a moderate amount of complexity can literally take hundreds of man hours of development time and skill beyond the ability of most classroom environments, which I think is why we underutilize these tools. So this is also why I started with a completed simulation in one of my classes. So what I've done here is come up with a basic full factory simulation. The box factory consists of a weight scale, sorting and transport conveyors, and a palletizing machine. It's got a, actually it's a little hard to see here, but there's a weight scale, there's a sorting conveyor, there's transport conveyors, and this is the stacking and palletizing machine here. And we'll talk more about these later. Now it's actually a combination of several scenes that are in factory IO with decking added and some conveyors to connect all the different scenes. I've included some extra proximity switches for position detection, and within this scene is full complete panels with push buttons and lights for manual and automatic control. So after this basic PLC training, though, what I do here is jump to the end of the project and give the students a taste of what a control system is like. Again, the goal is to provide a fully completed sorting and assembly line with all the inputs and outputs defined and configured. The operational parameters are laid out, and it has a fully functional PLC program and human interface. So what I created closely represents what a programming environment might look like, what a programmer in the field may be exposed to. Because students rarely, if ever, get to see a fully functional product that would help them give some clarity to the education when they're in the classroom. So remember back to the CAST concept of maximizing data transfer for comprehension. This is what I'm trying to achieve here. So as stated previously, the simulated environment must be attached to real hardware so the student can view or program an actual PLC, not just a simulated one. So this is the portable trainer I built with a briefcase style box, making it perfect for transporting or for use in a classroom with limited space. The Siemens S7 1200 programmable logic controller highlighted here allows me to include a complete system with fully automatic manual operation, conditions for fault messaging, properly formatted and commented ladder with different styles of programming, which is great for training, basic program block organization, as well as full symbols and rung descriptions. I lost track of the time I spent creating this code because it's again, it's well beyond what we can do in a classroom setting. The Siemens ComfortSoft TP700 HMI provided that ability to create screens for manual and automatic mode reset and selection, for displaying box weight, box count, sorting decisions, left, right, straight, etc. It allows for full manual control of the conveyors, the elevator, the palletizing system, and can show us all the status of all the inputs and outputs in the system. Again, a very realistic, fully functional control representation. Now also added here is an Ethernet hub for connection to all the devices, which by the way could be wireless, which is cool for industrial Internet of Things. And I do a demonstration using the S7 1200 built-in web server, and we'll talk about that more in the demo. I also mentioned here that I've added some basic fault messaging and history to this HMI to give that higher degree of realism. So from the setup perspective, give you a better idea of why this must be done ahead of time. What I'm showing here is an overhead view of the weight scale with the platform removed for clarity. The green tags indicate inputs, whether it's a proximity switch, an optical retroreflective sensor, diffuse sensor, whatever. The outputs are shown in orange, including the motors for the conveyors and the direction of the sorting ball table and the stack pole light. The blue shown here, down here, is the word containing the weight of the weight scale. Like I said, the boxes have weights. When they go on the weight scale, it reports a weight through that word. Now I've highlighted the extra inputs up here that I added, which were beyond the basic scene that I brought in from Factory IO. So a lot of this is done for you, and you just add what you need as you go along. The elevator portion I've tried to simplify here attaches to that end of that transport conveyor. It raises the pallets and allows the boxes to be stacked on these pallets. The inputs consists of elevator moving status, pallet entry, pallet loaded, pallet exit proximity switches. And there's, again, this is that example where I've added 2 switches for elevator lowered and elevator raised. So those are proximity switches that come with the simulation. And I'm using it to detect a moving object that's not like the box or the machinable material. As far as the outputs are concerned, there's a motor to raise and lower the conveyor, as well as one to move the pallets into the elevator via the chain conveyor. If we look at the top view of the elevator, we see that it's a box organizer. And along with the standard supplied inputs, I added pusher advance and pusher return proximity switches. Again, just a little addition to the standard scene. There's only one input for the model showing clamped advance and plate at limit. And this is where it allows me to demonstrate some different programming styles. So it's sufficient for what I need. There's a retroreflective sensor detecting parts before they enter the elevator pusher area. And every solenoid in here is single-sided. So when they're off, everything is back in its return position. And of course, you also have outputs for the belt feed and exit conveyors and the sorting conveyors. There is a warning light here. It comes on automatically as you raise and lower the elevator. So there are some built-in features here. Now, to add a little bit more realism to the simulation, some push button panels were added. And yes, I still have this fully functional HMI, and both that simulated panel and HMI can be used in the simulation to give the students a taste of basic push button control and also HMI control. The buttons are backlit, which means there are inputs and outputs associated with each of the buttons on the panel. And just a note here, each of these buttons are functional and can be manipulated by the operator when the simulation is running by use of the mouse. So that makes it really cool. Now I added a status display down here for box weight, box count, palletized layer setting, and layer count over here. And you can change these configurations either on the HMI or on the panel. So again, I'm showing both worlds here, HMI and panels. Near the elevator, I made an auxiliary control panel located on the deck. And this has no mode selection like a normal machine. Just a manual and a fault light for basic status. And as with the main panel, there's push buttons to start and stop the motors and control some of the motions. And the lights signify the status of each of those motions. And everything's live when the simulation is running, so you can watch the system operate. And you're going to get a better idea when we do the simulation. So finally, at the pallet entry and exit area, it has its own push button panel again, located at the bottom corner, where it's better to see the pallet conveyor, and the location of these panels is good at being able to highlight that we actually want to be within line of sight of the equipment that we're trying to control. And similarly, the pallet panel has manual control panels and status indicators like the other ones. And again, you have to build all these ahead of time, and it takes quite a bit of time to put these simulations together. The nice thing is, within the software configuration, all the inputs and outputs are accessible and set up as easy as just dragging and dropping any of these inputs over to the block that represents the PLC, or the outputs to the output represented on the PLC block. So it's fairly easy to do this configuration. I won't spend too much time on that. Now, having a fully programmed PLC program is one thing, but having a full HMI allows me to discuss design for the user. So I know this book is a bit dated, but the message is very applicable. The Design of Everyday Things by Don Norman explores the psychology of design and makes a couple of very important points about human memory and how we use technology. And with this in mind, I designed the HMI to be a more flat menu system, which I'll discuss on the next slide. Now shown here, right here, is part of a menu system I had the dubious pleasure of working with at General Motors, and was basically a spider web of interconnections and inconsistencies between menu buttons and functions. And even a diagram of a small portion demonstrates that a path that gets you to one screen is no direct path to get back to the main menu. There's inconsistency in menu buttons that makes it cumbersome and very difficult for the operators. Mr. Norman in his book discusses this type of problem and our tendency to switch to problem solver mode. When an operator gets confused, he or she starts going around just pressing buttons at random, looking for a solution. That's something we tend to do. After finding the solution, however, there's a good chance that we'll have no memory of how they achieved it. So this is not a situation we want to have on the shop floor. So now I have a chance to talk about designing for the operator. So I'm showing 8 of the 9 screens I created for the simulation. We have mode selection screen. We've got the elevator manual control screen, pallet conveyor control, weight configuration screen, which is also password protected. We've got our scale control and 2 screens for full input status and output status of all the words and IO in the system. And of course, our alarms and alarm history screen. So why is this a flat menu concept? Because all screens are accessible from each other. There's no searching for a screen. There's minimal operator training required. There's still password required to get into the settings screen, but that doesn't violate the flat menu concept. So this is a quick demo. And as you can see, by pressing any of the buttons along the bottom brings you to any available screen. The menu as well and the headers are all the same on every screen. And the concept here is that the screens are accessible from each other. Doesn't matter what your screen you're on, you can get to any screen without searching. So there's minimal operator training involved because all the information is available at a glance. There are some additional IO screens that are nested, but it's done without compromising that design for human concept. An operator can very easily operate this with very little training. And again, without a full simulation, this is a very difficult message to get across to the students. Now, one cool thing about the S7-1200 PLC is it has a built-in web server. With some very basic HTML code, I can create basic screens with some usefulness. The left screen on my phone shows the box count, the number of completed layers, as well as providing the counter reset function. The right screen is the mode and system start control screen with simple status or basic alarm messages displayed as a banner. And we have available automatic, manual, reset, run, stop, and system reset, just like we had on the main panel. And now what I tried to do here is keep that code simple with a very basic table format to display the data for the count screen. It allowed me to create the entire HTML code basically in one page. Okay, so this gives us the counter display, the reset button, and the button to switch to the next screen. The manual and auto mode control screen is very similar code with one extra level of complexity in the form of some JavaScript in order to display a header for the system and system status. Nothing fancy, again, trying to keep it simple. I only have one page of code that accomplishes the required functions for each of these screens. So as you can see here, or hopefully you can see here, the factory control on my phone is wirelessly communicating to my router back to the simulation through the PLC. And this might be difficult to see, but right now my phone is showing that the system is running and in automatic and in normal configuration. So this is all done wirelessly. Again, it's very difficult to demonstrate this unless you've got some sort of machine the phone can connect to. Now, if I generate a fault, the web page displayed on my phone will automatically update and show me that I have, in this case, an invalid weight fault. So using 3D simulation allows me to do a lot of things with the PLC, the HMI, IIoT demonstration that I can't do in a classroom setting with just the basic hardware simulation that we normally use. Okay, so now we're going to move on to a 15-minute presentation, and after that, I will take some questions. Thank you. Okay, I've brought the factory IO simulation up on my screen. You should see that now. And behind me, I have my my briefcase style simulator with the HMI and the PLC. And I'm going to switch over my camera to show you that a little bit more closely here before we start up the simulation. Okay, and sorry, I didn't have the camera in the right spot. Okay, so this is a close-up of the PLCs and the HMI that I have running. Now it's very difficult to see this HMI, so I have brought it up on my computer, and I want to use this to show you how the HMI functions, because this is a little bit more clear for the demonstration, and it also has the web page functionality running in the background there. So we'll get back to the HMI in a minute. I do want to show how the simulation works from the panel perspective. So we're going to go take a look at the main panel. We're going to zoom into the main panel here. And we're going to start up the conveyor system using the main panel. So we need to put it in automatic mode. And I'm going to start the system. There'll be a startup siren. And after the startup siren, all the conveyors will start and the boxes will start coming out to the weight scale. As you notice, all the indicators for the drives have turned on. You kind of have to zoom in a little bit to see the actual tags on these panels. So when I zoom out, you can't see that very well. Boxes come in, they're created by this emitter, and they're just randomly created. They go to the weight scale, they get assigned a weight, or the weight gets read, shows up on this screen here. So that was 10 pounds. This box is coming in at 8 pounds. And when the box comes in at the right weight, it's going to send it down this conveyor for palletizing. And of course, I'm not going to get a palletizing box the way I want. So we're just going to move on and wait for that palletizing box to show up. Once I get a palletizing box shows up, it comes down this conveyor. It actually gets moved into position with these diverters because the box doesn't line up perfectly along the conveyor. And again, perfect for simulation. Once the box gets to the pallet sorter, it will be put on top of this area here, clamped, and then the elevator will collect those boxes onto this pallet. And okay, finally we got one box here coming down the conveyor, and this is random, so it's, I can't force it to create those boxes. And as you can see, the box gets pushed around into the right alignment, which is very nice to see. If I take a look at this panel, actually it'd be easier just to do it this way. Right, that's the elevator panel, and it shows you the status of the elevator, the clamps, the pushers, all in real time. As you can see, the lights indicating the status and position of the objects in the simulation. Now, I talked about the objects being manipulated. If this box here was to get stuck, as an example, I can actually grab it and get rid of it. Say, okay, that was a bad box. Oh, here's another bad box. I'm gonna get rid of that one, right? Or I could create a jam up. Like grab this box and put it in here. Right now I have the wrong box down the conveyor. It's actually gonna jam the system up somewhere along the line. Maybe jam up the pusher if it gets all the way through, and you'll see a fault show up on the HMI later. So, something that a real operator could accidentally do, put the box down the wrong conveyor. So it makes it very nice real simulation. Now, what I can also do, I'm going to switch over here to the main panel display again, is if I stop the system, and now I've got a fault because I've stopped the system before box is transferred properly. So that's actually showing up as a fault. Can't see what the fault is here because it's actually on the HMI. So if you look at the HMI screen, you'll see a red flashing bar showing that there's a fault active, and that fault is the pusher advancing fault. So there's a good chance that if I go over to the elevator here, I'm going to see a jam up because I put that big box in the way. I now have that pusher. It never went all the way forward. Actually, that box got jammed up on that extra proximity switch I added. So now I'm stuck. Now the operator's stuck. He's in manual mode. He's got to clear this fault. So this is a perfect opportunity to take a look at manual control. So let's go make sure I'm in manual mode here. So hand auto reset, manual mode. We're going to go back. Now, because I reset, my pusher went back to its home position. I can take this box out of the way and get rid of it, throw it on the floor. This box may not be in the right position, so we'll get rid of that box. And now I can restart the system. Now, this system does have some issues because the counter thinks that there's boxes available for pushing. So when it creates another layer, it's actually going to be short boxes. And the operator would have to know that and maybe place a couple of extra boxes there. So anyway, if I'm in manual mode, Sorry, let me switch back to that panel. I can now control everything on the system manually. But just like any other system, if I just start turning it on, the boxes come down the conveyor, I don't have any way to sort them. They're just going to jam up. I've already created a fault, which is the pallets or the boxes getting stuck in this area. So, you know, if an operator doesn't know what he's doing, he's now jammed up his equipment because he hasn't started it up properly. Manual mode should only be for exceptional circumstances. So now he's really messed things up, and unless he stops, say emergency stops, the system will just keep running and he's stuck. I'll do a system reset. Okay, so let's take a look at the HMI for a second here. I don't know if you can zoom into the HMI control. Let's go over to my computer here. You'll see that there's a box stuck on scale fault. That's the fault that's come up. Okay. So I can reset that fault, and then I can put the system back in automatic mode, and then I can start same way as it worked on the panel. So I've set it up here so that the HMI and the panels in the system work concurrently. You can use either or, doesn't matter. And it shows how the HMI can provide even more information. So if I go to the weight control screen, I can now see the entry conveyor status. I can see the scale status, the left and right conveyors that they're on and running. And up here, I'm actually showing the input, the in proximity switch and the out proximity switch, showing the boxes going in and out of those certain areas. And it also has an indicator that there's a box on the scale. And as you noticed, everything is jammed up. I've cleared the fault, which means it's not going to reoccur unless you have software in to regenerate that fault. So now my system's stuck, but I can see on the screen nothing's moving. So I'm just going to get rid of all these boxes. Clear all these boxes off. Clear that box off. And we'll start over again. So some of these, all these faults are self-resetting once the system starts up again, and I get a box going down the left conveyor. That fault message will actually disappear. And I just did that for ease of control. If I go to my elevator control screen, again, I can see all my elevator statuses, the sensors, and the outputs. I can raise the elevator, advance the clamp, advance the pusher, advance and close the plate. Then I can see all these settings. If I go to the settings screen, which is password protected, maybe I shouldn't show that right now, I can actually set the different weights that are used for the weight control screen. Now off on the right side here, I've got my web server running. As if you notice, the web server says that my system is in automatic mode and it's running. And because everything works concurrently, I'm just going to put my HMI back in this mode so you can see it. If I stop here, everything goes into stop. So all this works concurrently and it works together, which is really kind of neat. So that web server is built into the Siemens S7 1200 PLC. And I don't know how easy it is to see on my phone. I have exactly the same thing on my phone. If you notice that fault came up, box stuck fault, it also came up on my phone. So because I'm running a simulation and I'm using a real PLC, I've got this option now to demonstrate all these cool things. I can have HMI control, I can have manual control on the floor, I can have just straight push button panel control, and you know, the sky's the limit in a lot of cases. So now on my phone, I can go ahead and do a system reset, right? And it does kind of expand again, unfortunately here. System's still in auto, and I can start it again. And once it's started, the phone goes back and tells me that I'm in run mode, same as the web server that I have running here on my computer. And all of this works concurrently, again, because you can do that programming in the HMI. Okay, so what we can do is demonstrate some manual motions here. So I'm going to go ahead and stop the system, put it into manual. Oops, have to hand auto reset. put it back into manual mode, and I'm going to go over to the elevator and demonstrate some manual functionality. I'll do that first from the panel. So I go to the elevator panel. Right, it actually has boxes on here, so this is probably a good time to demonstrate this. So the elevator's raised. I can advance the clamp. The pusher, if I try to advance the pusher, I'm going to jam up for this box, but the boxes are in the correct spot. So I'm going to go ahead and open the plate. And the plate's not opening. Great. Just making sure everything else is working. Oh. Didn't like when I pressed the button, that's all. So the plate is now opened. The boxes have dropped onto the pallet, and now I can lower the elevator. Okay, in this case, it's lowering all the way down. I can't create another layer. It's just going to go right to the bottom. And now I can go ahead and retract the clamp, close the shutter again. And if I wanted to, I could, oops, wrong button. This is where you can't read the button. Sometimes you need to zoom in a little bit. Sorry. And then you can advance the pusher and push that box, that lone box, onto the system. Okay, now I don't have control of the conveyors down here. I can only control them from this panel. And if you're in my projects class, I would show that it's very difficult to get to that panel from standing on the deck here. So I'm just going to zip over there quickly. All right, so now I can actually move these pallets out and into place. And you see it's pushing, and because I've messed up on how I turned the motors on, the vibrations are pushing the pallet, the boxes off the pallet. So again, they're reacting very much like you'd have in a real world simulation, or a real world where you've got pallets running into each other. I've pressed the wrong buttons. I've done the wrong thing here in manual mode, and kind of demonstrate how important it is to create a system that an operator can't mess up. So I probably should have had some sort of sequence of operation on this panel, or some way to lead the operator along, pressing the correct buttons to make this work. Now I can also do this on the HMI concurrently. If I go over to the pallet control screen, I can do the same here. I can turn all those motors on. Same as I did on that panel. So again, it all works concurrently. And then I can turn them off again. Now, the nice thing about the HMI is I can show, and this is something we do in industry as well, is show the status of all the inputs on the system. So there's 2 pages of inputs. That's how many inputs I have coming into the PLC, and 2 pages of outputs. So now I can see the status, the actual raw status of all the inputs and outputs. And again, something we like to see in industry, and I can demonstrate that because I've got this full simulation. If I go over to the alarm screen, because I had some alarms, I now can show alarm history. Pallet stuck on elevator, we had one of those. We had the pallet stuck on scale, so I can see when the alarm occurred and when the alarm was cleared. I had a box stuck on the left conveyor, we saw that, and again, when the alarm was created and when the alarm was cleared. So now the operator has, or the student has the ability to see how faults get created and how to deal with them. And traditionally in the classroom, we can't show this with just a basic PLC simulation, and you can't have a student program all this. There's just too many hours. They can program like a little piece of it, but they can't see the whole big picture. So again, what I've given the students is a fully completed factory with a fully programmed HMI, fully programmed PLC. It has IIoT functionality with a web server. I can do it wirelessly to my phone, and demonstrates basically as much as I can in a single small factory. And I think at this point, we'll take some questions.
Welcome, everyone. I'm Stephanie, an OSPE board member. I will be helping to facilitate the Q&A for Wayne. The first question is, Wayne, you mentioned you spent time working abroad in Thailand. Can you tell us about a distinct career memory or experience you had while working as an engineer outside of Canada?
I almost forgot to turn my microphone there. Can you hear me okay? I was on mute there for a second. So well, let's keep this on the theme of teaching. While I was in Thailand, General Motors went through its bankruptcy period. And it was a very stressful period for us because we stopped construction on the plant. We had no money to do anything with. We had no money for training. We had no money for basic office supplies. We had to beg, borrow, and steal from our sister plant in Thailand. And I was trying to think, what can I do with my engineers to keep them interested and keep them on board, basically. And so what I came up with, and it's not exactly the right one, but we started using Lego robots to teach engineering. So I actually had 10 kits because we wanted to start up a Lego league in Thailand. So I had 10 of these RCX units, and we brought them into the classroom, and I used this to teach programming. Because it really doesn't matter what programming code you're teaching in, half of your programming is planning. So we did a lot of planning, what the robot was going to do, how it was going to go along the table, follow the lines, use the sensors. And then the next half of the class was them having some fun programming. And afterwards, the biggest question they had is, can we have another class? Can we have another class? Because they loved it, because it was hands-on, gave them something to do, some like goal to shoot for. So if I said, okay, this robot needs to follow that line, use the sensor on the bottom. I think this one, okay, this one doesn't have it. So use the sensor on the bottom to follow a line on the floor, and they loved it. Traditionally, what we do in the classroom is, we press a button, there's a timer and light flashes. We might simulate a traffic signal, something like that, but it's not of interest to the students. So when they had something that they could program, it had a task, and something that they could see work, then they had that sense of accomplishment. And they really wanted to get back to using this style. And the programming for Lego robotics is fairly intuitive and fairly simple. So they didn't really have to learn a lot of new programming skills, but I did go through a lot of training on, how to plan to do your program. So just from an education, there's lots of memories from Thailand, but just from an educational standpoint, we spent, a few months playing with the Lego robot, teaching programming skills. So that's kind of one of my most favorite memories, because we're thinking, how are we going to do this? We got no money, we got no resources. Like, oh, I got Lego kits. And I thought everybody was going to go, oh, Legos, what are you doing, Wayne? But no, they really took to it, and they were very, very interested and had a great time.
A great memory. Thanks, Wayne. Okay, second question. This person works in mining, and our simulations are typically just in Excel and not very visual or intuitive. We would have automated loaders, conveyors, storages, etc. Would 3D simulation software be customizable enough to simulate a mine?
The software I'm working with right now, I think you could simulate some basic functionality. I don't know if you could simulate an entire mine operation, but you could simulate aspects of that operation. And the goal with the simulation isn't to try to model a factory exactly like the factory is going to be programmed. The intent of the simulation is to show aspects of programming that the student normally wouldn't see in the program. So for example, I was showing the manual and auto operations, resetting manual mode, creating fault messages. That's common regardless of what system you're using. So you could set up a basic load unload operation here in this simulation that may not necessarily exactly be your mining conveyors, but you could still simulate the same ideas, the concepts you need to teach. And even in General Motors, and actually I started researching this while I was at General Motors, trying to find a way to teach my electricians code without being at a machine and without being in the classroom, because classroom is very limited, like, say doing it in Excel, or, just putting it on a PowerPoint, or we have trainers with, again, go back to the push buttons and lights, and that really doesn't show them what the factory is doing. How do I generate a fault? If I have a fault, what page do I go to in the PLC to find where my fault messages are? So I can create samples that simulate environments that are very similar. So I think you can. I think you can, as long as you're relating whatever program you've come up with, those concepts, you need to relate that back to the real world somehow when you're talking to the operator. In my projects class, I talk about what I said in the demo. If you don't train the operator how to start the equipment up properly, this is what can happen. They can turn the conveyors on, the boxes jam up. Now you've got a big problem on your hands. and you can simulate those kind of environmental issues. So I think you can have some basic mining concepts using even this simple simulation, and they are coming up with some upgrades. I'm very interested in seeing what they've added over the years.
Great, thank you. Are the walkways mainly for visual accuracy to real assembly lines, or do they serve any function to the simulation?
They do serve function in the simulation. I can share my screen here for a second. Let me just share that. Okay. Can you see my screen okay?
Yes, we can.
Okay, so if I go to what they call first person view, where now the operator is walking along the floor, okay, I can only get to that control panel by going up this set of stairs. Okay, so now I can see I can get to this control panel with that set of stairs. It also shows if I want to get to this control panel in the background, the only way for the operator to get there, and again, I do this in projects class, as he or she has to walk around this whole system to get to this panel. And again, you may not have any choice. Maybe that's just the way your system's going to set up. But what I was trying to show in the demo is once I've manipulated the environment up here, I've opened the shutter, I've dropped the boxes, I've cleared the jam, I've returned the pusher. I want to start up, but I got to get rid of that pallet that was down here. And I look over here, and there's in the background the conveyor for, or the control panel for these conveyors. So what's the operator have to do? Well, the operator now has to turn around and he has to walk all the way back. And this is the functionality of those rails. If I don't design the system properly, this operator is walking all the way around to get to this panel. So now this is from a project planning standpoint, which really wasn't the topic here, but from a project planning standpoint, it shows, if I don't have a set of stairs to get up and down to this panel, then now I've created a hazard for the operator because he's got to walk all the way around. What if he tries to jump over this because it's a shortcut? And same if I now walk back and I say, okay, let's start the system back up. And this is a real world scenario. He comes up this set of stairs and he realizes that he's now blocked. And I can guarantee on night shift or afternoon shift, he is going to hop on that conveyor and he's going to go over here to this panel. He is not going to walk around. So now I've designed for failure. So we can use simulation not just to teach programming, but we can use simulation to teach project management, proper panel placement, concepts like that.
Very good. Okay, I have one more from here. This question is a little out of topic, but can you please suggest any skills for which new graduates in mechanical and industrial engineering should work on? Any certifications that could help them get a job? Because I'm disheartened seeing every job posting asking for a minimum 5 years experience. So some help here for the audience would be helpful. Wayne.
Yeah, and we have this discussion in class because what I teach in what we call the Industrial Automation Grad Cert program. So all of the students I have in my program right now have gone through and received their engineering degree either in Ontario or another country, and they've come to Niagara College to get that hands-on experience. And they go for their job interviews and they ask me that same question. Well, okay, I've got this hands-on experience in the lab. What's that good for? And so then you sell yourself. You say, I've spent 5 to 10 hours or more, 20 hours on an ABB robot doing programming, move the programming around. I'm familiar with the pendant, I'm familiar with the operation, but then they need to go further and leverage that and say, although that's only the ABB robot, I know how this can be used to apply to a FNUC robot. Because as engineers in the field, we're required sometimes to read the manual on the fly, figure out what's wrong with the system that we've never seen before, and try to help fix it. So you need to sell yourself by saying, I've got the base of robotics and I can apply that to any robot in the field because now I know how robots work and robots think. Same with a PLC environment. You can say you've got, say 20, 30 hours hands-on experience programming in a simulated environment. And now it's up to you to sell yourself to the employer on how that applies to a real factory and how you can use those skills to apply yourself to a real factory. And when I was interviewing students, if they had come in with that kind of explanation, said, listen, I know how to use Rockwell, I know how to use Siemens PLCs, I've done more than just push button and light simulation, I know how automatic and manual circuits work. And all I wanted from those engineers was I didn't want to have to teach them how to get into a PLC. If they knew how to get in, they could work with an electrician and help problem solve and just get that basics. And I wouldn't necessarily require the 5 years of PLC training necessarily. You know, as long as I knew they had the basic concepts and that background, sometimes that was good enough for me when I was hiring. But yeah, it ends up being how you sell yourself and leverage all this work you've done in the classroom and in the lab and say, that's your experience. You may not have specific work experience, but doing work in a real world and doing work in a lab, you can now argue your point.
Some very practical advice. Thank you, Wayne. I have one more question here. What is one piece of advice in the same vein? What is one piece of advice you would commonly offer to your students or young technical professionals starting out in their careers?
Other than being totally honest in their interviews, you can use other experiences in life to sell yourself in an interview. I'm not an interview expert by any means, but I did a lot of things in my youth. I did a lot of work throughout my university career, where I volunteered with other organizations, and I would bring that up in the interview as a way to show the interviewer that I was more than just an engineer, that I was an engineer that had community outreach experience, that had volunteer experience, that was more well-rounded from that standpoint. Because as an engineer, you're dealing with people as well, not just equipment. And in my case, I was managing people, so managing other engineers, and I was also a liaison with our maintenance groups, our other management groups, how to talk to other managers. So there's a lot in engineering that's not just hands-on a computer doing programming. There's a lot of people you have to interface with. So I think emphasizing those people skills also helps quite a bit.
Yeah, I have to agree with you there. So thank you, Wayne, for a very informative session. Thank you to the audience for attending. Please head to your next session starting at 9:30 and visit the agenda tab in the left navigation menu to access the links. Thank you so much.
Thank you so much for having me.